Hello students, welcome to the next session of graph theory. In the last lecture, we have done with the planar graph. In this lecture, we will cover shortest path algorithm, and the name of the algorithm is Dijkstras algorithm. See, what is Dijkstras algorithm? It is used for finding the shortest path between any two vertices in a graph. So it works well on both directed as well as on undirected graph. But the compulsory condition is that all nodes, it must have no negative weight. So it does not work on the negative weight. A weighted graph, it associates a label or the weight with every edge in the graph. So these weights are usually in the form of real numbers. Now, what are the application of Dijkstras algorithm? First application is Google Maps. These are the best example of real life network. In real life, we always want to know what is the shortest path between two places. So in any of the map, each town is a vertex or a node, and each road is an edge or an arc. Even the computer cannot decide which route is the best route, so it uses an algorithm to do so. One such algorithm is there. The name of the algorithm is Dijkstras algorithm. See, first example, we will study it for the directed graph. Next, we will study it for the undirected graph. So see, the question is, we have to find out the shortest path from the source vertex. What is the source vertex here? A. To all the vertices and print the path as well. So see, the starting vertex is A. Distance from starting vertex to itself is 0. So that's why this is the step number 1. Total 5 number of nodes are there: A, B, C, D, E. A to A distance is 0. Right now, all the other nodes are at infinite distance. So that's why I am here writing it at infinite. And in this way, we have to write out the path, whichever path we are going to follow, or we can say that whichever node we are going to put up in the final state, that we will write out one by one. See, now distance from, we are going to put up the A node into the final state. So that's why here we are writing it as 0, and all the other nodes are at infinite state. Next, here you can see what are the adjacent nodes of A. Adjacent nodes are B and C. So these are the red lines. We can see it, and here we are writing the distance. What is the distance we have to follow whenever we want to travel from A to B or from A to C. So see, A to B distance is 10. So that's why this node is in the final state. Final state means till now A has been reached. Now we have to move on further. So adjacent nodes of A are B and C. Update the weights of those adjacent nodes into the table. So A to B distance is 10. A to C distance is 3. Moving further. Now, prior to move further, we have to decide out of these all nodes, which one node is having the very less value, means minimum weight. By minimum weight we can proceed further. So what is the minimum value here? 3. So we will put up next into the final state which one node? C node. So see here, after A I am going to put up which one node into the final state? C. So here I am writing A comma C. Now next, what are the nodes which are adjacent to this node? Currently, which one I am putting it into the final state? So the next node, that is C, and the adjacent nodes are B, D and E. See, it's here. Whenever we want to move to this node, means to B node. So 3, here till now the distance is 3. So 3 plus 4 is how much? 7. So is 7 is less than 10? Yes. So that means we have to update the weight. If the weight is more than 10, then we couldn't able to update it. So see, in the next step, same way, whenever we want to move from C to D, then in that case 3 plus 8, how much? 11. So that's why here I am writing it out 11, here I am writing it out 7. And this one node, that is E node, total distance is how much? 5. Now, my question is that we want to put up any of the node into the final state. So we will decide on the basis of their weights which one node is having the minimum weight we will put up into the final state. So the node is E. So next we will put up E into the final state and the path is here ACE. Now next node we will see out of the pending nodes which one is having the lesser weight. See it here, either through E. Is there any node whose weight is getting updated? So first we will check it. E to B there is no such connection, but E to D there is a connection. If we want to update the weight, see here the weight is 5 and we have to add 9, then in that case our weight will be 14. So is 11 less than 14? Yes. So that means the older one weight will remain same. So that means 11 will remain same. And in this case 7 is same. So out of both nodes weight, which one is the minimum? 7. So we will put up B into the final state. So here this is the path. Now which one is the pending node? Only E, and the weight is, we will check it either through B node. Is this weight is getting lesser than the earlier? See, till now the weight is 7 and we will add 2, 9. Yes, 9 is less than 11, that's why we are going to update it. So that means D node weight is 9. Now the final path is ACEBD. Now in this way we are able to find out the shortest path from the source vertex to the all other vertices, and we have printed the path as well. So in the next example we will study it for the undirected graph. Yes, in this example we have to find out the length of a shortest path between the vertices 0 and 5 in the weighted graph. This is the undirected graph starting from node 0 itself. Means 0 to 0 distance is 0 and all the other nodes are at infinite distance. See, we are processing this node. Now 0 plus 4 is less than infinity. Yes, it is less than, so update the weight 4. Next, for this node 2, if 0 plus 3 less than infinity, yes, it is there. So that means we will update the weight of this node. So the distances for this node is 3. Now what are the adjacent nodes to this node? See it here, 3 and 4. Out of 3 and 4, which one is having the lesser weight? 3. Now first we will put up 0 node into the final state and then we will process which one node is having the lesser weight? This one node. So we will put up this node also into the final state. Now we will move on through this node to this node. So the distance through this is 3 plus 1 is 4 and through this side it is also 4. So I don't think so there is so much again issue. Now in this case 3 plus 3 for the fourth node, what is the final distance? 6. 6 is less than infinity? Yes, it is okay, 6. So for this case 3, what is the final weight? 3 plus 4, 7, 7 less than infinity? Yes, it is there. So that means we will update the weight of this node. So final weight is 7. So next is, now out of these 3 nodes 1, 3 and 4, which one node we have to put up into the final state? First we will put up 1. Now next, which one node we want to move it into the final state? Either 1, either 2, 3 or 4. So we will put up 2 into the final state because its weight is very less. So we will process this node. So if we move through this node, then our weight get updated. That means our weight is 6. Yes, 6 is less than 7. That's why we are doing it like that. So now we will put up this node into the final state. Yes, it is okay. Done. Next is 6. Here weight is also 6. We can take it out any node first. For example, we will take it out 4. So process this node and update the weight of 5 as well as update the weight of 3. So we are going to update the weight. Till now the weight is 6. 6 plus 2 is 8. Yes, older one weight is less. So 6 will remain same. Here the weight is 6. For this case, 6 plus 6 is 12, 12 less than infinity. Yes, it is there. So that means our final weight for this node is 12. Now, we will put our 4 node into the final state. Right? After that, we will process the next node, that is 3. So, we are going to process this one node. So, we are processing it here. Now, next one node, you can see it here. Till now the weight is 6, 6 plus 1 is 7, 7 less than 12, yes, absolutely true. So in this case, we will update the weight of this node. Our final weight, final distance to this node is 7 and the path is, we will put up 3 node into the final state. So our final weight is 0, 1, 2, 3 and 2, 5. So this is the final answer and we will process this node. Thank you very much. In the next lecture, we will cover Max Flow Ford Fulkerson algorithm.